Science is often driven by beautiful ideas born from desperation. In the early 1930s, physicists faced a crisis. Beta decay seemed to violate the law of conservation of energy. It was as if the universe had sprung a leak. Austrian physicist Wolfgang Pauli proposed a radical solution: an invisible neutral particle carrying away the missing energy. He called it a desperate remedy, a particle that couldn't be detected. Italian physicist Enrico Fermi embraced Pauli's idea, building a theory around it and naming the particle the neutrino, the little neutral one. For over 2 decades, the neutrino remained a theoretical ghost. That changed in 1956, when Clyde Cowan and Frederick Raynes used a nuclear reactor to finally detect neutrinos. Their massive detector caught the rare flashes of a neutrino interacting with matter. The ghost was real. Pauli's desperate idea became a cornerstone of modern physics. The hunt for the neutrino secrets had truly begun. From a crisis in physics, a new chapter in our understanding of the universe was born. The neutrino, once a mathematical trick, became a fundamental piece of reality. And so began one of science's greatest detective stories. What gives the neutrino its ghostly reputation? 3 key traits. First, it has no electric charge, making it invisible to most detectors. Second, it interacts only via the weak nuclear force, so rarely that trillions pass through you every second unnoticed. A neutrino could travel through a light year of light and still have only a 50-50 chance of hitting anything. They are the ultimate cosmic travelers, carrying information from the heart of stars and cosmic explosions. Third, their mass is tiny, at least 1 million times lighter than an electron. For years, physicists thought neutrinos might be massless, but experiments proved otherwise. This minuscule mass has huge consequences, shaking the foundations of particle physics. Neutrinos are elusive, but their properties make them perfect messengers from the universe's most extreme environments. Their very existence challenges our understanding of the cosmos. There isn't just one kind of neutrino, there are 3, each paired with a charged lepton, electron, muon, and tau. For decades, physicists thought these flavors were fixed, but neutrinos have a quantum trick. As they travel, they can change from one flavor to another. This phenomenon is called neutrino oscillation. An electron neutrino from the Sun can arrive on Earth as a muon or tau neutrino. It's like throwing a red ball and having it land as blue or green. This shape-shifting is a direct result of quantum mechanics and the fact that neutrinos have mass. Each flavor is a mixture of 3 mass states, like a musical chord blending 3 notes. As neutrinos travel, the mix changes, and so does the detected flavor. This discovery shattered the neat, tidy picture of the standard model. Neutrinos are not just elusive, they're unpredictable. Their oscillations reveal a hidden complexity in the subatomic world. The universe, it turns out, is far stranger than we imagined. The first clue to neutrino oscillation came from the Sun. Experiments detected only 1/3 of the expected electron neutrinos, till the Sudbury Neutrino Observatory showed the missing ones had changed flavor. Atmospheric neutrino experiments, like Super Kamikande in Japan, found muon neutrinos vanishing after traveling through Earth, evidence they transformed into other types. Particle accelerator experiments confirmed this transformation in controlled settings. Neutrino oscillation was no longer a theory, it was a proven fact. The standard model once required neutrinos to be massless. Their mass and oscillations revealed a crack in this near-perfect theory. Neutrinos may get their mass from a mechanism unlike any other particle, perhaps linked to a hypothetical heavy partner, the seesaw mechanism. This hints at physics beyond the standard model at energy scales we can't yet reach. Neutrinos are the first experimental evidence for new physics. They are not just another particle, they are a signpost to a deeper theory. Every answer about neutrinos leads to even bigger questions. They are the loose thread that could unravel a whole new tapestry of reality. Neutrino oscillations opened a Pandora's box of mysteries. We know neutrinos have mass, but not their exact values or ordering. Do they violate CP symmetry, helping explain why the universe is made of matter? Is there a fourth, sterile neutrino, and even more elusive ghost? Are neutrinos their own antiparticles, blurring the line between matter and antimatter? Each question could revolutionize our understanding of the universe. Neutrinos are central to the biggest questions in cosmology. Their properties may explain why matter dominates over antimatter. If they violate CP symmetry, they could have tipped the cosmic scales in our favor. Sterile neutrinos might be the dark matter that shapes galaxies. Even their tiny mass influences how the universe's structure forms. By studying neutrinos, we probe the history and fate of the cosmos. They are a fundamental ingredient in our models of the universe. Understanding them could unlock the secrets of existence itself. To solve these mysteries, scientists are building massive new experiments. The Deep Underground Neutrino Experiment, DUNE, in the US, will fire neutrinos 800 miles underground, searching for CP violation and mass ordering. In Japan, Hyper Kamiokande will study neutrinos from many sources with unprecedented precision. These projects will cross-check each other's results, giving us confidence in new discoveries. Meanwhile, experiments like LEGEND and NEXO hunt for neutrinoless double beta decay, seeking to prove if neutrinos are their own antiparticles. These efforts require patience and ingenuity, but the potential rewards are immense. The hunt for the neutrino's true nature is one of science's greatest quests. The neutrino's story began as a desperate idea and became a central mystery of physics. It's a tale of wonder, perseverance, and the relentless drive to know. Neutrinos are cosmic messengers, carrying secrets from the sun, supernovae, and the Big Bang. They let us peer into hidden realms and test our deepest theories. The questions they raise are among science's most profound. The standard model is not the final word. Neutrinos are our guide to new physics. As trillions pass through you every second, remember, the hunt for their secrets could rewrite reality itself. The ghost Pauli imagined still haunts us, not as a problem, but as a promise of discoveries yet to come.